combustion, what's going on inside our cells, metabolism, rust. These and many other examples of reactions are of a certain type. And in this type of reaction, they're called oxidation-reduction reactions. And in these reactions, there's an exchange of electrons between their reactants. There's an electron producer and there's an electron acceptor. For example, copper reacts with oxygen and air to form copper oxide, and that kind of tarnishes the metal. But you can reverse this reaction with a torch. So the substance that's oxidized loses the electrons. Copper, in this case, loses the electrons to oxygen in the air, and we form copper oxide. And then you can reverse the reaction by applying heat. So in this type of reaction, one reactant is producing electrons, the other reactant is accepting them. So we need to keep track of these electrons, and how we're going to do that is assigning each element an oxidation number. So here's the rules. Here's the first rule. Elements. The oxidation number of an atom, of an element in its natural state is always 0. For example, iron solid, its oxidation state is 0. Each atom of nitrogen in N2 gas is 0, because those are the natural states of those elements. Rule 2. Monatomic ions, single ions. The oxidation number of the atom in a single ion is always the charge. So if you have chloride anion, its oxidation state is a -1. Iron 3, its oxidation state is 3. Oxygen. Oxygen is pretty much always -2. So in this case, you have diphosphorus pentoxide. Oxygen is always -2. And sodium oxide. Oxygen is always -2. Now here's oxygen in its elemental state, so there it's 0. Hydrogen. The oxidation number of hydrogen is almost always +1. So in hydrochloric acid, +1. Hydrogen, but in its natural state, it'd be 0. Halogens. Remember, these are the halogens. Fluorine, chlorine, bromine, iodine. Do you remember what their charge is when they form an ion? They're 1 away from the nobles. They all form -1. That's a big hint on their oxidation state. All the halogens are always in -1 oxidation state. So fluorine in this compound, its oxidation state is a -1. Fluorine in its natural state would be 0. Compounds and ions. Now this is an important one. Once we have a general idea of what the general oxidation states are of certain elements, the sum of all the oxidation numbers must be 0, or the charge. So in this case, diphosphorus pentoxide, 2 phosphorus atoms and 5 oxygen atoms, their oxidation states all have to add up to be 0, because that's the charge on the compound. It's neutral. With phosphate, the 4 oxygens and the single phosphorus atom, they have to add up to be a -3, because that's the charge. Let's try it. We know that oxygen is always -2. I'm going to circle my oxidation states. 5 times -2 is -10. So just from the oxygens alone, I have a -10. So the phosphorus has to be a +10. And I have 2 of them, so each phosphorus has to be a +5. See, the oxidation state of phosphorus is 5. The oxidation state of oxygen is -2. Let's try it with phosphate. Now my charges have to add up to be a -3 when I'm all done. So each oxygen is a -2. Again, I'm circling my oxidation states. 4 times -2 is -8. So phosphorus, whatever it is, has to add up to be a -3 when I add it to a -8. So +5. +5 and a -8 is a -3. So phosphorus is a +5 again. Oxygen is -2. So let's try a few of these. Determine the oxidation number of each element in each compound. So I'm going to be circling my answers here. Oxygen is -2. 2 times -2 is -4. So sulfur has to be +4. Oxygen is -2. 4 times -2 is -8. We did this one already. Phosphorus has to be positive 5. Hydroxide. Oxygen's always negative 2. Hydrogen positive 1. And it works. Positive 1 and negative 2 is a negative 1. Ammonium chloride. Let's start with the chlorine. Chlorine has to be negative 1. And remember, nitrogen is always positive 1. 4 times positive 1 is positive 4. And I've got a negative 1 from the chlorine. So I've got a positive 3 so far, so nitrogen has to be a negative 3. Iron 2 nitrate. Remember, this 2 is coming from the iron, so iron has to be a positive 2. Now nitrate is really NO3 minus, right? So each oxygen is always negative 2. 3 times negative 2 is negative 6. Nitrogen has to be what? Positive 5. It's a positive 5 and negative 6 would be a negative 1. Calcium perchlorate. Calcium has to be a plus 2, right? How about perchlorate? Oxygen's always negative 2. 4 times negative 2 is negative 8. So chlorine has to be what? What plus a negative 8 gives a negative 1? Positive 7. So just to clean that up, calcium is a positive 2. Chlorine is a positive 7. Oxygen's a negative 2. Potassium carbonate. Potassium is in group 1. That's going to be plus 1. Each oxygen's a negative 2. It's going to be a negative 6 total. So what does carbon have to be? I've got 2 potassiums, so I really have a plus 2 here. I only have 1 carbon. Has to be a positive 4. Lithium thiosulfate. So lithium is a positive 1. It's in group 1. We really have 2 of them, so we really have a positive 2 over here. Oxygen is always negative 2. 3 of them, though, so I have a negative 6. Now this sulfur. Now I realize I have 2 sulfurs. So whatever it is, I have to add it to a positive 2 and a negative 6. I better get 0. So this has to be a positive 4, right? Because 4 and 2 is 6, and negative 6 would be 0. But I have 2 of them. So each sulfur has to be a positive 2. Manganese oxide. I've got oxygen, always negative 2. That'd be a negative 4 total. Manganese has to be a positive 4. So I should have said manganese 4 oxide would be the best name I can give it. How about this one? Chromium has to be a positive 3. Sulfur, a negative 2. Let's look at the subscripts. Strontium iodate. Strontium has to be a positive 2. And then my iodate, each oxygen's a negative 2. 3 times negative 2 is a negative 6. So iodine has to be a positive 5. Because 5 and a negative 6 would give me my negative 1. So we should write those out. Strontium is a positive 2. Oxygen, a negative 2. Iodine, positive 5. Some useful electrochemistry terminology. When a reactant gets oxidized, its oxidation state changes as it's being converted to product and becomes more positive. For example, circle the reactant that gets oxidized. Okay, is it going to be iron or is it chlorine? Well, let's start out. First, we know their oxidation state for both of them is just 0 because they're in their natural state. Over here, iron becomes a positive 2, chlorine becomes a negative 1. So which one gets oxidized? Which one gets more positive? Iron does. So circle iron. When a reactant gets reduced, its oxidation state changes as it is being converted to product and becomes more negative. Reduction. For example, circle a reactant that gets reduced. Well, we already said iron goes from 0 to positive 2. That's getting more positive. Chlorine is going from 0 to negative 1. chlorine is getting reduced. Oxidizing and reducing agents are always reactants. And in general, you can always say oxidizing agents get reduced, reducing agents always get oxidized. So for example, circle the reducing agent. So the reducing agent got oxidized. Iron went from 0 to a positive 2. So this compound, it got oxidized. So it is the reducing agent. And circle the reducing agent. Label the oxidizing and reducing agents for each unbalanced redox reaction. Okay, let's pick out tin is easier because we know tin is 0, and over here tin is a positive. So this compound, it got oxidized. If it got oxidized, it's the reducing agent. So if tin is the reducing agent, nitrate has to be the oxidizing agent. There's nothing really easy in this one, so let's just start. Oxygen's -2. 3 times -2 is -6. Sulfur has to be +4. So what is sulfur on the other side? Oxygen's always -2. 4 times -2 is -8. Sulfur is +6. So this compound, it got +4 to +6. It got oxidized. So that means it is the reducing agent. So this compound has to be the oxidizing agent. Okay, how about this one? Notice chromium on the product side is +3. So all we got to do is figure out what chromium is over here. Oxygen's -2. 7 times -2 is -14. Now I have 2 chromiums. Each one has to be a +6. Because 2 times +6 is +12. And a +12 and a -14 is -2. Okay, so this compound, it got what? It got reduced. So this is the oxidizing agent. This must be the reducing agent. So I think the name of the game here is pretty much this table right here. If you understand how to determine the oxidation state of the different elements in a compound, you're set. Just remember the compound that gets oxidized is the reducing agent. The compound that gets reduced is the oxidizing agent.